Assalamualaikum and hello to everyone. So in this video tutorial, we will look at one question from chapter 6 involving gas powered cycle for the application of internal combustion engine. So in this video tutorial, we will look at an example for the Otto cycle, which is the ideal cycle for a spark ignition engine. So we have here an Otto cycle. The compression ratio is 9.5. So compression ratio here is RV. So RV here is equals to 9, or RV equals to the maximum volume at state 1 divided by the minimum volume at state 2. So the compression ratio is 9.5. Prior to the isentropic compression, meaning at state 1, so the air is at 100 kilopascal, 35 degrees Celsius, and 600 centimeter cubic, the volume in units centimeter cubic. And then the temperature at the end of the isentropic expansion process, so at the end of the isentropic expansion process, so this is state 4. State 4, isentropic compression process just now was state before, prior, so prior means before, so this is state 1, prior to the isentropic compression process. The second one just now was at the end of the isentropic expansion process. So state 4 is 800 degrees Celsius. So this is the temperature at state 4. So sketch the PV diagram and determine, A, the highest temperature and pressure in the cycle. So the highest temperature and pressure in the cycle, if we know the PV diagram, for an Otto cycle, so let us sketch here the PV diagram of the Otto cycle. So we have here state 1, isentropic compression, to state 2, constant volume heat addition, to state 3, and then isentropic expansion to state 4, and then constant volume heat rejection to state 1. So this is the PV diagram for the Otto cycle. So as you can see, the highest, or the maximum state for the cycle is at state 3. So the highest temperature and pressure here refers to T3 and also P3. Based on the PV diagram, we can see that state 3 is the highest state. Of all the 4 states available, state 3 is the highest. And then the second one is the amount of heat transfer in units kilojoule. So the amount of heat added to the cycle. So the amount of heat added here is at process 2 to 3, the constant volume heat addition. So here is the Q in, in capital letter because the unit is in kilojoule. And then the thermal efficiency, so thermal efficiency is the, and then number 4 is the mean effective pressure, or MEP, in units kilopascal. So we can start with step number 1. So for step number 1, we try to draw the schematic diagram for the Otto cycle. So we start with state 1. So this is prior to the isentropic compression process. So state 1 here, we know that the pressure 100 kilopascal, temperature 35 degrees Celsius, and volume 600 centimeter cubic. So we can state it. So pressure is 100 kilopascal. Temperature is 35 degrees Celsius. So we can add with 273 So this will give us 308 Kelvin. And then we also know the volume. Okay, so 600 centimeter cubic. We can convert it into meters cubic. Okay, so 0.0006 meter cubic. Okay, so this is basic mathematics. Okay, so make sure you know how to convert centimeter cubic to meter cubic. Okay, and then we have state 2, which is the isentropic compression. So the piston has to go down. Okay, so this is state 2. Okay, so this is the isentropic compression. Alright, so isentropic compression, okay, we don't know the pressure, okay, we don't know the temperature, and we know that the compression ratio V1 over V2 is 9.5, so we can actually calculate the volume at state 2. Okay, so volume at state 1 was 0.000006 divided by 9.5. So here we can get the volume, okay, at state 2. Okay, so the volume at state 2 is, we can calculate. Okay, so if I'm not mistaken, the volume at state 2 here is 0.00000632 meter cube. Okay, so this is the volume at state 2. Okay, we can find, and then we have this state 3, which is the constant volume. So the position of the piston is the same as state 2. Okay, so this is state 3. Okay, the pressure at state 3 we don't know, we have to find. The temperature at state 3 we have to find. The volume at state 3 is the same as the volume at state 2. Okay, because it's a constant volume heat addition process. So the process here is the isochoric heating. Okay, and then we have the third process, which is the isentropic expansion. Okay, so the piston rises back. Okay, and the position of the piston at state 4, okay, has to be the same as the position at state 1. Okay, because it's a from state 4 to state 1 later will be the constant volume heat rejection, isochoric heat rejection. So that's why the position of the piston has to be the same. Okay, so but the pressure first. Okay, we don't know the pressure. We know the temperature. Okay, 800 Kelvin. Okay, and the volume is the same as state 1. Okay, so we know the values. All right, and then for the, so this one is the isentropic expansion. Okay, and then the final process, okay, to make it a full cycle. Okay, from state 4 here, we return back to state 1. Okay, by isochoric, okay, constant volume heat rejection. So isochoric cooling. Okay, because we are rejecting heat, so we have to cool the substance, okay, back to its initial position. Okay, so this is step 1. Okay, try to draw to see that you understand the question. Okay, so next will be the properties. Okay, step number 2. Okay, so for the first item, we know that we have to find the temperature and pressure at state 3. Okay, so these are properties at state 3. Okay, so number 2, we have to find the amount of heat added. So this is Q in. Okay, so Q in process state 2 to 3. Okay, is equals to mCV, constant volume process, T3 minus T2. Okay, So we have to find the value for M, the temperature at state 2, and also the temperature at state 3. Okay. Number 3, we have to find the thermal efficiency. So thermal efficiency is the work net produced by the cycle divided by the amount of heat added. Okay, so we have already calculated the amount of heat added. So we have to calculate the amount of work produced, net work produced. So work net here is the same as the amount of heat added minus the amount of heat rejected. Okay, so we have already calculated the amount of heat added. So let's write the formula for amount of heat rejected. Okay, so MCV T4 minus T1. Okay, so we have the calculation Q in and Q out, so we can calculate for amount of net work produced. Alright, number 3. And then number 4 is the mean effective pressure. So mean effective pressure, since we have calculated the amount of net work produced, W net, capital letters, so we divide it with the maximum volume, the volume at state 1, minus with the minimum volume, the volume at state 2. Okay, so these are the equations. Okay, so we know which properties we have to find. Okay, so for step 3, we find the required properties. So we start with state 1. So state 1 just now, we know the pressure, 100 kilopascal, we know the temperature, 308 Kelvin, and we know the volume. Alright. So from the equation just now, we know we have to find for the value for mass. So at state 1, using the ideal gas equation, P1 V1 equals to MRT1, so we can calculate for the mass. Okay. So substituting the values. Okay. For R, since the substance is air, so the R is 0.287. Okay, and the temperature is 308. So this one we can calculate, and we can get the mass answer 0.00068 kilograms. Okay, so that is all for state 1. State 1 here. Okay. Next we go to state 2. So from state 2, we have to calculate the temperature. Sorry. Okay, the temperature at state 2. Okay, T2 here. So we know it's an isentropic process. Okay, so we can use, okay, before that we know that V2 is 0.0000632. Okay, since it's an isentropic compression process, we can use the isentropic relationship equation for gases, okay, involving temperature and also volume. Okay, so T2 over T1 is equivalent to V1 over V2 by the power of K minus 1. Okay, so V1 over V2 is also RV, okay, K minus 1. Okay, so to find for T2 here, we have to substitute the values. So T1 multiply with the compression ratio, K minus 1. Okay, so 308. Compression ratio is 9.5. K for air is 1.4. Okay, so here we can get the value for temperature at state 2, 758. Okay, I have rounded out the value. Okay. Okay, next is to calculate, okay, the pressure. Okay, so try to calculate the temperature and also the pressure at each state. Okay, at each state. Okay, so for pressure, we can use the isentropic relationship equation, P2 over P1, V1 over V2 by the power of K. Okay, so P2 here equals to P1, V1 over V2 is RV by the power of K. So P1 was 100 kilopascal, RV was 9.5, K is 1.4. So we can see here that P2 is 2338 kilopascal. Okay, so that is for state 2. Okay, I go on to a new slide. So for state 3, okay, so we have to find here the temperature and also the pressure. We know that the volume is the same as state 2. Okay, sorry. Okay, so first we try to use P3, V3, MR3. Okay, we try to use this one first, but we don't have pressure, we don't have temperature, so this equation cannot be used yet. Okay, so once the ideal gas law cannot be used, we try to relate with the process. Okay, so there are two processes involving state 3. The first process is from state 2 to state 3, which is the isochoric process. Okay, and then we have from state 3 to state 4, which is the isentropic process. Okay, so we can choose either one. Okay, we can try to solve using the isochoric process first. If cannot, then we can try for the isentropic process. Which one is easier? Okay, so if we understand properly the question, okay, let's try, okay, for trying sake, from process 2 to 3. Okay, let's just check. Okay, so isochoric process. Okay, so using the combined gas law, okay, P2 V2 T2 over P3 V3 T3. So isochoric process, the volume is the same. Okay, but when we check, okay, we have pressure, we have temperature at state 2, but we don't have the pressure, we don't have the temperature at state 3. So the first process cannot be done. Okay, so we try for the second process, okay, from state 3 to state 4, which is the isentropic process. Okay. Okay, so for isentropic process, using the isentropic relationship equation, so we have T3 over T4 equals to V4 over V3, okay, K minus 1. Okay, and V4 over V3 here, okay, is the same as V1 over V2. Okay, so which is the compression ratio, okay, RV, for an Otto cycle. Okay, so we can solve for T4 here. Okay, sorry, we can solve for T3 because T4 we know. Okay, we know the value for T4, 800. So T4 times with RV, K minus 1. So we can find 800. Okay, 9.5, 1 minus 4, 1.4 minus 1. So we can find the temperature at state 3 here, 1969 Kelvin. Okay, now to solve for the pressure, we can use, okay, the combined gas law. Okay, so P2, T2, we want to calculate for P3, we have already calculated T3. So using the combined gas law, we can solve for P3, okay, which is P2 T3 over T2. Okay, so P2 just now we have already calculated 2338. Okay, T3 was 1969. Okay, and T2 was 758. So this should get around 6073 kilopascal. Okay, so we have already solved for the first item from the question. Okay, at state 3. Okay, next we go to state 4. So state 4. Okay, we know the temperature. Okay, Kelvin, and we know the volume is the same as the volume at state 1. Okay, if we want to calculate for P4, we can try, but we don't have to, okay, because we don't require the value for pressure at state 4. So once all the properties required is known, we can proceed with step 4. Okay, so for step 4, let me add another slide. Okay, first, alright, for step 4, we just have to substitute and solve. So for number 2, we have to find the amount of heat added. Okay, so mCv T3 minus T2. So Cv here for air. Okay, so Cv here for air is 0.718 kilojoules per kgK. Okay, so mass was 0.00068. Okay, Cv is 0.718. Okay, 1609, and T2 was 758. So this will give us, okay, depending on the number of decimal points. Okay, so this will give us the answer 0.59. Okay, approximately 0.59 kilojoules. Okay. Then number 3, okay, we have to calculate for the thermal efficiency, okay, which is the work net divided by the amount of heat added. So we have already calculated Q in, so we have to find for Q out first. So Q out equals to mCv T4 minus T1 as written before. So 0.00068, okay, 0.718, 800 minus with 308. Okay, so this one will give us around 0.24 kilojoules. Okay, so for work net, it's simply the amount of heat added minus the amount of heat rejected. So 0.59 just now minus with 0.24 will give us 0.35 kilojoules. Okay, so replacing the values, okay, back in the equation, so 0.35 divided by 0.59, so will give us in a ratio form, okay, will give us 0.593 or 59.3%. Okay, so this is the answer. And then finally for mean effective pressure, MEP. Okay, so number 4, MEP is equivalent to the amount of net work produced, V1 minus V2. So we have already calculated work net 0.35. Okay, so for volume 1 is 0.006 minus volume 2 is 0.000632. Okay, so this will give us approximately, depending on the amount of decimal point, okay, the answer 652 kilopascal. Okay, so this is the example, additional example or tutorial for Otto cycle. So thank you for your attention and have a good day.